So this question is about a baby monitor that has a sensor unit that transmits an image of the baby and the noises the baby makes to a monitor unit. The monitor unit then displays an image of the baby and emits the noise the baby makes. Compare the properties of the waves that transmit images and noises from the monitor unit. So we're looking for something that transmits images and we're comparing that to the noises. So the images is going to be about light, and the noises is going to be about sound. So we need to compare both light and sound, and this is the type of question you're going to get in a new exam where they're going to really test your understanding from the question. So images being light, if we were to compare the wave of light, we're going to talk about a transverse wave. Okay, and transverse waves travel at 3 times 10 to the 8 meters per second. And the oscillation of a transverse wave, the vibration, remember, is perpendicular to the direction of energy transfer. What does that mean? Well, if you remember, the wave moves up and down, so the oscillation of the wave is moving up and down, and the energy moves at a right angle. So we've got this wave that looks like this. The wave is actually bobbing up and down, and the energy is going through the center at a right angle. Okay, so it's a transverse wave, and it makes this T for transverse because the wave's going up and down. The oscillation of the wave, sorry, is going up and down, and the energy is moving at a right angle. In terms of sound, well, sound is a longitudinal wave. And longitudinal waves in terms of sound travel at about 330 meters per second, depending on the air itself. So denser materials will travel at a faster speed. So if it was a solid, it would travel much faster than it would in a liquid, and a liquid would travel faster than it does in a gas. So in air, roughly speaking, sound travels at around this speed. And when you're describing a sound wave, again, you use the term oscillation. So the oscillation is parallel this time. So it is parallel to the direction of energy transfer. And remember, a wave is something that transfers energy. What do I mean by this one? Well, we're getting bands this time, like in this diagram here, and the bands are then going to vibrate backwards and forwards, and these will be the sound waves, backwards and forwards. So the oscillation is going from left to right, left to right, left to right, and the energy is traveling parallel to this. So these two lines are parallel, and these lines are perpendicular at right angles. The next question says the sensor unit can detect infrared and visible light. Suggest one advantage of being able to detect infrared. Well, if it's a sensor unit and it's used for a baby monitor, then it will be able to be used at night time. So the usefulness of this is you can see the baby at night. Write down the equation that links frequency, wave speed and wavelength. Remember, V is our wave speed, and that is equal to F times lambda. So V is the wave speed. Now if you're asked to write it down, don't write the letters like I've done. You need to write the whole thing out. So wave speed is equal to the frequency multiplied by the wavelength. And while we're here, we'll do the units. So that is in meters per second. Frequency is in hertz. Remember, it's a capital H, lowercase z, and wavelength is in meters. They are the units, and you must write the whole thing out. Right, the next question says the signals for the baby monitor are transmitted as electromagnetic waves with a wavelength of 0.125 meters. Calculate the frequency of the signal. So we just said V is equal to F times lambda. So our next equation for frequency, we're going to have to rearrange this equation. So remember, if V is equal to F times lambda, and we need to move lambda, we're going to divide by lambda on both sides. That will cancel out, so F is equal to V divided by lambda. Now remember, lambda is wavelength, so it's the speed divided by the wavelength. What is the speed? 3 times 10 to the 8. and we're going to divide that by 0.125, and that will give us 2, 4, and we're going to have 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros. So when you're writing this, it's too long a number, so you look at the numbers after the first digit. There is 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be 2.4 times 10 to the 9 hertz. So remember, if we use standard form, it just makes it a little bit easier to understand. Right, the next question says sound waves cause oscillations in the air. Sound waves are longitudinal, which we've described before. In which direction are the oscillations? Remember, oscillation means vibration of the particles compared to the direction of energy. They are parallel. The diagram shows the disturbance of air molecules in the path of a sound wave. Label the diagram with the letter R of a rarefaction. So the rarefaction is this region here. So rarefaction is when the sound particles are moved apart, so the particles in the air. Label the diagram with the rarefaction, and next show a complete wavelength. So we could pick from the very center of a compression to the next center of a compression, and that would be a wavelength, or we could pick from the center of the rarefaction to the center of the rarefaction, and they should be the same wavelength, so that would be a wavelength. So I'm going to label that wavelength like so. I'm just going to put on there C. It's not on the diagram, but sorry, it's not on the question, but this is equal to a compression, and you need to know that for your exam. So a compression is when all the particles are close together, and a rarefaction is when they are far apart, and the wavelength is from one identical point to the next. The next question says, on the diagram shows the wavelength, so we're going to pick one point and go to an identical point, and we're going to draw our wavelength. We could pick the top to the top. Remember, these are the peaks and these are the troughs. So if we were to label this wave, the bottom would be the trough, the top would be the peak, and if we draw an axis through the center, we can now put the amplitude on, and the amplitude is from the center to the top or from the center to the bottom. So this is the displacement of the wave. So we've got maximum displacement from the center to the top, and that is the amplitude. So amplitude is labeled A, and the wavelength we need to label W. The wavelength of the wave is 0.1 meters. We're trying to calculate the speed, so we know V is equal to F times lambda. The frequency is 2 hertz. It's 0.1 meters in length, so that will give us 0.2, and that is in meters per second. Don't forget the units. After a person is injured, a doctor will sometimes ask for a photograph to be taken of the patient's bone structure. What type of electromagnetic radiation would be used to take the photograph? Remember, these are X-rays. Describe the property of this radiation which enables it to be used to photograph bones. Well, X-rays penetrate skin and muscle tissue. So why can we see them? That's because X-rays are absorbed by bone. So this property of being absorbed by bone but passing through the rest of the tissue is really important, and that is what's picked up by the scanner. Right, so the next question, we've got a speed gun firing microwaves, and then the microwaves are reflected when they hit the tennis ball. Complete the following sentence. So we can see by the diagram the difference. The wavelength of the microwaves reflected. Well, look at this wavelength. You can see the wavelength is clearly decreased compared to this one, so that is going to be shorter than. Complete the following sentence by drawing a ring around the correct line in the box. When the ball absorbs microwaves, its temperature. If it absorbs any energy whatsoever, it must increase slightly. So there is an increase in overall energy of the ball, so that causes an increase in temperature. The energy increase may cause vibrations in the ball, so these kinetic vibrations in the ball are going to increase the overall temperature. Right, the next question says, describe the pattern that links the difference between the two frequencies and the speed of the ball. So we can see here we've got the difference in frequency in hertz, and as we increase that, we're increasing the other. Now remember, when you talk about a graph, the first thing you do is talk about the independent variable, which is here, and then talk about how it relates to the dependent variable. So what are we doing? We're increasing the independent variable, so increasing the speed of tennis ball. So when I've talked about this, I'm talking about exactly what is said on this label. As I increase the speed of the tennis ball, what am I doing to this? I am increasing the difference in frequency in hertz. Increasing the speed of tennis ball increases the difference in frequency in hertz. You can clearly see I've talked about how increasing one thing increases another thing. The second point, it's only for 1 mark, is this is directly proportional. It's really important that you recognize when it starts at 0, 0 through the origin and you get a straight line, that is a directly proportional graph. The speed gun measures the difference between the two frequencies as 3,200 Hz. Use the graph to find the speed of the tennis ball and show clearly on the graph how you obtained your answer. Okay, so for this question, if we go across from 3,200, which is there, I'm going to draw a nice line across, and it's going to meet there. So I draw a line down, and that is at 20 meters per second. Okay, which one of the following gives the reason why the data is shown as a line graph? Right, frequency and speed are both categoric. Well, that's not true. So categoric means that you can write them into categories. When we go back to our variables, speed is not a category and frequency is not a category. Frequency and speed are both continuous variables. Well, we know they're continuous because there can be any number between them. Remember, the continuous variable means it could be an infinite number between variables. And what do I mean by that? Between 10 and 20 speed, there could be an infinite number of speed. So 10 could go to 10.01, 10.0001, and this could go on forever. So between 10 and 20 there is an infinite number of possibilities. So this is a continuous scale. Both frequency and speed are continuous because there is an infinite number of scales between the numbers. Right, electromagnetic waves have many uses. The diagram shows two ways of sending information using electromagnetic waves. And you can see a satellite in space and the atmosphere surrounding the Earth. What type of wave is used to send information to and from satellites? Well, to penetrate through this layer, you would need microwaves. Here we can see another type of wave. This is a radio wave. Radio waves are reflected off the atmosphere, and we need to know also what this part of the atmosphere is called. So we're going to do this in a later question. So what type of wave is used to send the information? Microwaves. What property of this wave makes it suitable for satellite communication? Well, microwaves can penetrate, which means pass through, so they can penetrate the ionosphere. And what does the ionosphere mean? The ionosphere is the part of the atmosphere that is charged, so it is the charged region of the atmosphere. So if we have gases in the atmosphere such as oxygen, and oxygen becomes O2 minus, or if we had hydrogen and say hydrogen was H plus, they are both charged gases. They could be in the ionosphere. So these charged gases make up the ionosphere because an ion is an atom that has gained or lost electrons. You can see they become charged. Right, use information in a diagram to describe the connection between the frequency of a radio wave and the distance the radio wave travels through the atmosphere. Well, at low frequencies, they not traveled very far and then they become reflected. At medium frequency, they've traveled up to about 120 kilometers from the surface and been reflected. At very high frequencies, we've got up to about 280 kilometers. So what's the relationship? Well, at higher frequencies, the radio waves travel further through the atmosphere before being reflected. Okay? Right, electromagnetic waves travel at 300 million meters per second. And remember, if we looked at this number, there are 8 zeros after the 3, so that is 3 times 10 to the 8 meters per second. A radio station transmits wavelengths with a wavelength of 20 meters. So radio waves are the biggest waves in the electromagnetic spectrum, and from one point to another, that wavelength would be 20 meters. So we're now trying to calculate the frequency. Well, we know that V is equal to F times lambda from before. So F must be equal to V divided by lambda. So V is speed, that is the wavelength. So we're going to do 3 times 10 to the 8, and we're going to divide that by 20, which is our wavelength, and that will give us 15,000 kilohertz. Okay, so where have I got 15,000 kilohertz from? Well, the actual answer is going to be equal to 15 million. So this is 15 million hertz. A kilo is 1,000 times larger. So I need to remove these 3, and that will give me my 15,000 kilohertz. Okay, so 15,000 kilohertz is the same as 15 million hertz. And if we went any further, we could say that 15 megahertz would be the same as 15,000 kilohertz or 15 million hertz. So remember, we go mega is 1,000,000, kilo is 1,000, and then we've got hertz. So remember, you have to know these prefixes for your physics exam. Right, the next question. Waves may be longitudinal or transverse. Describe the difference between longitudinal waves and transverse waves. Well, we talked about this before. Longitudinal are sound waves, and sound waves, the oscillation or vibration. So the oscillation or vibration travels parallel to the direction of energy. Now, a lot of mark schemes recently have also asked you to talk about what a sound wave looks like, so you need to talk about actually its properties. So always write this down just in case. So sound waves contain rarefactions and compressions. Remember, there's never any harm in giving more information to make sure you always get the full 3 marks. Transverse waves, give an example to start with. So light, all electromagnetic waves are transverse. So remember, we've got radio waves, microwaves, infrared, visible light, UV, X-rays and gamma rays. All of these are transverse. They all travel at the same speed. What is that speed? It's 3 times 10 to the 8 meters per second in a vacuum. For this question, really though, we need to talk about the oscillation. And the oscillation, remember, which is the vibration, travels perpendicular to the direction of energy. Right, radio waves, electromagnetic waves. Describe how radio waves are different from sound waves. So we know radio waves. So radio waves are transverse, as we've just discussed, by the electromagnetic spectrum, and they travel at 3 times 10 to the 8 meters per second in a vacuum. So in space, that's how fast they travel. Sound waves are longitudinal, and they cannot travel in a vacuum. They are also much slower, travel at 330 meters per second in air. Remember, this is in air. They travel faster in solids and a little bit faster in liquids. So the transmission of longitudinal sound waves is to do with how close the particles are together, and that's why they would travel faster in a solid. Okay, the next question says, what does a frequency of 440 Hertz mean? It means there are 440 waves per second. So in 1 second you have 440 waves. The sound waves produced by the keyboard travel at 340 meters per second. Calculate the wavelength of the note. Well, we know that V is equal to F times lambda, and this time we're trying to find the wavelength, which is lambda, so that must be equal to V divided by F. We've just worked out that, it tells us that the speed is 340 meters per second, and we're going to divide that by the frequency in the question above, which is 440. So what does that equal? That equals 0.772 727, and this is recurring, so this number keeps recurring. So we need to do it to 3 significant figures. So these are our 3 significant figures. However, the number after the 2 is higher than a 5, so we're going to have to round that up to 0.773. So that would be our answer to 3 significant figures. Right, the last question talks about a microphone connected to an oscilloscope. Now remember, oscilloscope is one of these machines that transmits any electrical impulse into a wave. So we're getting this wavefront on a screen, and the wavefronts look like this. So the first note you can clearly see has quite a low wave, so that means the amplitude is low, and here the amplitude is higher. So that's what we can see from the picture. So it's asked us to give us 2 conclusions from the notes played by this keyboard. Well, conclusion 1 would be to do with the amplitude. So sound in figure 2 is quieter than figure 3. The reason, the amplitude is smaller. Remember, this amplitude means a quiet sound, and this higher amplitude means it's louder. As the sound wave's got more energy. Right, conclusion 2, well, there is 1, 2, 3, 4 waves here, and here there is 1, 2.5 waves. So conclusion 2, figure 2 has lower frequency than figure 3. Reason, oscilloscope screen. We'll call it oscilloscope screen 3 has more waves in same time frame. So this is really important. There are more waves in the same amount of time. So whatever time frame this is, there's 4 waves, and in whatever time frame this is, there's 2.5 waves. If it was in 1 second, then it'd be 2.5 waves per second. So the frequency would be 2.5 Hertz. If this was 4, it'd be 4 Hertz. So the frequency clearly is higher here because there are more waves per second. Right, so here are all the answers to the mark scheme. So if you just wanted to go through these, I will leave them up for about 5 seconds for each one.